Hello, my name is Stephanie Passo, and today I'm going to present the classification of cardiac arrhythmia with intra and interpatient paradigm using the transfer learning. If you all want to see my code, you can go to github.stephanie and arrhythmia classification. All right. So, before anything, what is cardiac arrhythmia? Cardiac arrhythmia is related with the cardiac abnormal heartbeat according to the bad working of electrical signals that coordinate the cardiac pulse. For example, we have the pulse of the P wave. When the P wave have a abnormal heartbeat, it means that the atreus had some sickness. We need to figure out what is happening in the atreus of the heart. In the KRS complex, when this KRS complex have an abnormalia, we should figure out about the ventricles of the heart. And the same thing about the T wave, we want to see the recover wave, what is going on when happen the recovery of the heartbeat, okay? And we see that this problem of abnormal heart sickness affects around 175 millions of people every year, and these atrial fibrillations can make a lot of hospitalizations in the United States every year, for around 750 million hospitalizations, okay, for year. And this sickness have the highest, is the second highest mortality rate, and it is potentially fatal if we detect it in a very advanced stage. And for this, we want to make it observable and detect it when the sickness is not that advanced, all right? And for this, the objective of our research is to classify the cardiac arrhythmia according to the variation of the ECG heartbeat using the machine learning method with the neural network. In this way, we don't need exactly a professional to see the heartbeat. We also have a previous evaluation, a probabilistic model to figure if that heartbeat have a sickness or not, and if it have a sickness, if it have a arrhythmia, a cardiac arrhythmia, the patient can go to a doctor and manage it better and see how good what can they do to make themselves better and healthier, right? And also, the purpose of the solution is to enable and develop a system to a continuous monitoring of the patients. In this way, the person can detect this arrhythmia and figure if they are sick or not, and have this continuous monitoring anytime with wearables, for example. But also, when we use medical data, we need to observe the intra and intra patient, which paradigm. These paradigmas say that when we have segmentations of a patient, and we put part of the segmentations for a train and for a test, and the same patient is in the segmentation of this patient is in the train and also in the test, we say that this separation of the data have bias, because it's just like when I put the same picture in the train and the test, and when we are trying to evaluate that model will get an evaluation bias of the data, and maybe the accuracy will not be necessarily just good as it's supposed to be when we evaluate the model with this kind of intra-patient paradigm. But the inter-patient paradigm say that we should separate the data between patients. Then I say that the patient blue will stay, the segmentations of the patient blue will stay just in the train, not in the test. In this way, the train have different patients from the test frame, and then we can evaluate our model with a more real world duty. Okay, like in the intra patients paradigm, we have segments from the blue patient in the train and also in the test. But in the inter patient, the blue patient is just presented on the train part, okay? And looking for this, the state of arts, most of them evaluate their model with the intra-patient paradigm, where have this bias of the patient segmentations. But just Mosef did this classification and this evaluation with the inter-patient data set, okay? But Kashue did a transfer learning, and for our project we also want to do a transfer learning evaluating in an inter-patient and in the intra-patient paradigm. Kashue just evaluated in the intra-patient paradigm, where the paradigm have kind of a bias from these data, okay? And here we want to show our architecture. The transfer learning is just like this. We have the ECG data, we segment it, and we put it on our probabilistic model, which will do the classification, and all of these weights, these trainable weights, are just sent to transfer their learning for another model, and this other model will learn another task with the baseline, with the PTB baseline, and do the classification of the PTB baseline, okay? The first baseline we use the MIT, and the second one the PTB. And here we see that the MIT baseline have around 5 classes according to the Association of Medicine, and the PTB baseline database have 2 classes with a myocardial infarction and other classifications, other arrhythmias. And for each of these ECG samples, we did a cutting window or segmentation of 10 seconds. Every 10 seconds, we just cut each ECG classes to have the samples and do the training. And this training is, or these data are sent to our model, our probabilistic model, which we have here the feature extractions in a kind of a recurrent network because of this loop. We use also the dropout to delete some of the neurons and make our feature extractions work harder to understand their data. And also we have the batch normalization and the totally connected layers, with are the dense layers here, and do the classification at the end. And also we can see that when we use the intra-patient paradigm, which is the paradigm where I have kind of a bias in our data, we see that our model get a learning of 91% of accuracy, and the baseline, which is Kashue, did a 90% accuracy, which is not a big difference, but it's okay. And when we use the inter-patient, where we don't have bias in the separation of the data, we say that our network did around 81.21% of accuracy, and the baseline 81.12. And when we get these models and do the transfer learning for the intra-patient, where the data have kind of a bias in their separation, we say that the baseline got 99.95% of accuracy. But our method didn't had a very good accuracy according to the baseline, but when we use the inter-patient, where we don't have bias in the data, our model get the highest accuracy, which is 81.81% of accuracy. Okay, and looking for this, our future work is to test a data argumentation and learn the transfer method, increase the accuracy in the minority classes, balance the base, and also compress the model and ship it to a wearable. In this way, we can do this detection and figure about our patients better. Okay, then I think this. Thank you for the attention, and Soli Deo Gloria.